about telling this story, we need to move time backwards, really backwards. More precisely, 13.82 billion years ago, when all that is around you, when all the matter in the universe, when the whole universe was resumed to this singularity. Then, suddenly, Big Bang. Let's freeze time right there. Something about 10 seconds right after Big Bang. We have a couple of numbers to take a look at. So our first number is the half-life time of a neutron. That is 887 seconds. Something about 15 minutes. Actually, a neutron is not stable by his own. He needs to be bound to a nucleus to be stable. Other way, if he's not bound to a nucleus 887 seconds after being formed, he disintegrates into quarks. Our second number, scientists estimate that something about 10 seconds after the Big Bang, the density of the universe was 1 ton per cubic centimeter. So let's imagine that this is the universe when he was 10 seconds old. Scientists know that back then the universe was made only by elemental particles. So what happened to a bunch of elemental particles become what we see today? The answer is nuclear fusion. It consists in binding two nucleus together in order to create heavier elements. Problem is that nuclear fusion is a very hard reaction to make. So we need two things for nuclear fusion to happen: very energetic particles and a very high density. So let's take another look into our early universe model, and let's add a little bit of energy like in the early Big Bang. As you can see, because of the high density, it's a very messy and chaotic place, very energetic, perfect for nuclear fusion to happen. We know that protons are both positively charged, so whenever we try to push them together, they repel. And actually, the first step of nuclear fusion is binding a neutron with a proton. You have deuterium. Problem is, as it's very simple to bind them together, it's very simple as well to break them apart. And this takes us to our last number, and actually the most problematic one of them. Back then, in the early universe, the energy needed to keep deuterium together was slightly lower than the average energy of the photons at that time. Whenever the deuterium was formed, he was instantly destroyed by one of the 1,000 energetic photons that were traveling through space at that time. Well, we have pretty much a race here, because we need to bind neutrons before 15 minutes or they will disintegrate. And no neutrons means no elements besides hydrogen. It will be a universe only made of hydrogen. So we have a really hard problem here. We know that the universe is expanding. The Big Bang is expansion. So the universe was expanding since we started this story. So if our universe was this big 10 seconds after the Big Bang, now our universe is this big. So here we have our universe 1.5 million after the Big Bang. So you can see that the density has dropped a little bit. It's not longer the same messy and chaotic place that it was when the universe was just 10 seconds old. It is still pretty messy and chaotic, and actually nuclear fusion keeps happening, but not in the same way that when 10 seconds old. It is due to the density change. The photon's average energy dropped below the binding energy of the deuterium. So we finally can bind a neutron with a proton to create deuterium, and deuterium finally can stay formed. So nuclear fusion is finally happening. But as I told you when I explained nuclear fusion, it consists in binding two elements together to create heavier ones. But if the nuclear fusion keeps going on, we'll finally have iron. That is the most stable element. So we will live in a universe made only of iron. So the laws of physics appears once again to finally save the day. Well, the expansion kept going on while we were telling this story. So if the universe started this big when it was 10 seconds old and became this big when he was 1.5 minutes old, something about 3 minutes after the Big Bang he was this big. So here we have finally our 3 minutes old universe. We can see that the density has dropped so far that the nuclear fusion finally stops, and it stops in the right moment, allowing neutrons to bind with protons so that we could have heavier elements in the future, but without allowing all the elements to combine into iron. Today, the universe is made by 75% of hydrogen, 25% of helium, and obviously a tiny amount of other heavier elements. Scientists have realized that this amount of hydrogen and helium that we see today is what was left from the primordial nucleosynthesis. 3 minutes after the Big Bang, the universe was basically made of hydrogen and helium, heavier elements, like the carbon in our bodies, like the calcium in our bones, like the iron in our blood, or like the oxygen that we breathe, will only appear a couple of million years later when the first generation of stars light up and allow nuclear fusion in their nucleus. Then, in the end of their lives, they will explode in a supernova and spread all these life ingredients to the universe. And these life ingredients, with another huge thousand of coincidence, would end up into this. That is why we are stellar dust.